So let me get this straight. You're telling me I can complete the month.
R4 learns two potential paths it can use to get to that 10.0.1 network, either through R3 or R5. R3 is 3 hops away, R5 is only 2 hops away, so it is the route via R5 that is going to make it into the routing table because it's got the best metric. Both routes will be there in the RIP database, but it's only the best one that actually makes it into the routing table, which is the one that's got the lowest metric. So R4, like I just explained, says I learned those two possible routes to get to the 10.0.1.0/24 network. 3 hops via 10.1.1.2 out interface fast Ethernet 0/0. 2 hops via 10.1.3.2 out fast Ethernet 2/0. And it puts the best one in the routing table, which is via R5. So if we do the show IP route, we see just that one best route via R5 has made it into the routing table. Okay, so that was how RIP works with the hop count as its metric. Let's look at the metrics for the other routing protocols as well. I don't need to go through it step by step for these other ones though. So you saw a problem there with RIP. If I go back a couple of slides, the top path in our network topology is all 100 meg links, but the bottom path is only 10 megabits per second links. So really we would prefer the traffic to go across the top path. But because RIP uses hop count, the traffic is always going to go along that worse bottom path. So let's see how it works with OSPF as compared with that. So OSPF does take bandwidth into account. It uses cost as the metric, which is automatically derived from interface bandwidth by default. You can also manually configure the cost of links if you want to manipulate the path, but OSPF is typically going to take the best path anyway. And in our example, it is going to prefer the path from R4 to R3 to R2 to R1 for the 10.0.1.0/24 network. So unlike RIP, which used hop count and went along the bottom path, which we didn't want, OSPF is going to use cost, which takes bandwidth into account, and it's going to go along the top path because those links have got much higher bandwidth. So if we have exact same topology and we enable OSPF on our interfaces and do a show route, you'll see that traffic will go across the top path. Traffic is going out interface fast Ethernet 0/0 from R4, which is the top path. ISIS also uses cost as the metric, but unlike with OSPF, it's It's not automatically derived from the interface bandwidth. All links have got an equal cost by default. So if you want to force a particular path to be used in ISIS based on which path has got the best bandwidth, you're going to have to manually configure that. It's not going to do it automatically like OSPF does. If you don't manually set the link costs in ISIS in our example, then the lowest hop count will be used, which was the bottom path in our example again. So again, it's going to use path R4 to R5 to R1 by default in ISIS. Now in ISIS, you can manipulate it to go along the top path. In RIP, you're not really able to do that. The last IGP we have is iGRP, and it uses the bandwidth and delay of links to calculate the metric. Load and reliability can also be configured. But they're ignored by default. So bandwidth is used the same as it was with OSPF. We also have delay as well. But the way that iGRP works, it's not like it's sending probes over the links to measure what the delay is. It uses a fixed delay, which is based on what the bandwidth is. So basically it's based on the bandwidth again. You can manually configure the delay on links if you want to manipulate the path. So with OSPF and iGRP, because it is going to use the best bandwidth links anyway, typically it's going to choose the path that you would want it to. But if for some reason it's not, you can override that with manual configuration. And in our example, again, it's going to use the top path because those are the higher bandwidth links. It will use that path by default. So last slide, let's consider how we would choose a routing protocol. Like I said before, you do not want to be running multiple routing protocols inside your organization. Because it's going to get messed. With OSPF and iGRP, because it is going to use the best bandwidth links anyway, typically it's going to choose the path that you would want it to. But if for some reason it's not, you can override that with manual configuration. And in our example, again, it's going to use the top path because those are the higher bandwidth links. It will use that path by default. So last slide, let's consider how we would choose a routing protocol. Like I said before, you do not want to be running multiple routing protocols inside your organization because it's going to get messy. It makes things hard to work with each other. Organizations will almost always standardize on one protocol. Really, the only reason they would have multiple different protocols is if there was a merger or was some kind of historical or political reasons for it. Okay, so we're going to choose one routing protocol. Comparing them, RIP uses hop count and has a default maximum metric of 15, so it's not usually used in production networks because of its scalability limitations. EIGRP is very simple to maintain. Calculates changes very quickly, and its metric calculation will normally choose the best path by default. It is, however, typically only supported on Cisco routers. It was originally completely Cisco proprietary. Cisco made moves to open it up a while ago, but it's still mostly only supported on Cisco routers. So it kind of forces you into using all Cisco routers if you're going to use EIGRP. OSPF's metric calculation will typically choose the best path by default, like EIGRP. It is an open standard which is supported by all vendors' routers, and because of this, it's the most commonly deployed IGP today. It is, however, more complicated to maintain than EIGRP. And finally, ISIS links need to be manually configured, or it will use hop count to determine the best path, which is not usually what we want to happen. It's typically only used in service provider networks. or large organizations with their own MPLS network who choose it because of its scalability. Okay, so because of this, it really comes down to either EIGRP or OSPF for most organizations. EIGRP is the simplest one to use and it works great, but you can really only use it if you're using only Cisco routers. OSPF also works great as well, but it's more complicated to maintain. It is, however, supported on all vendors' routers. Okay, so that's everything I needed to tell you about metrics. Let's have a look at how it works in the lab next. In this lecture, we're going to take a look at how our IGP metrics work in the lab. I've got the same usual setup for this section with my 5 routers, R1 to R5, and the IP addresses are already configured. I've got no routing protocols and no static routes configured. The first IP addresses, verify that, and the IP addresses are already configured. I've got no routing protocols and no static routes configured yet. Let's just verify that. So at the command line, you can see I've done a show IP interface brief, and there. In this lecture, you'll learn about equal cost multipath, ECMP. If multiple paths to a destination network have an equal metric, the router will enter all of those paths into the routing table and it will load balance the outbound traffic to that destination network over those available multiple equal cost paths. And all routing protocols, all your IGPs will perform equal cost multipath by default. So RIP will do it, ISIS, EIGRP, OSPF, they will all do equal cost multipath by default, meaning if they learn multiple paths to get to the same destination and those paths have got the same cost and it's the best path, it will put them all in the routing table and load balance across all of those paths. So they can all do equal cost multipath. EIGRP is the only routing protocol that can do unequal cost multipath. So they'll all do equal cost multipath by default, including EIGRP. EIGRP will not do unequal cost load balancing by default, but it can do it if you manually configure it to do so. So looking at our example here, we have got R1 on the right, we've got R4 on the left. And the example is going to take a look at how R4 is going to get to the 10.0.1.0/24 network behind R1. And if you look in our example topology, all of the links are the same bandwidth. They're all 100 megabits per second, and it has to go through 1, 2, 3 100 meg links along the top path, and also 1, 2, 3 100 meg links along the bottom path. So all of our different routing protocols would see these two paths, top and bottom, as being an equal cost path. So in that case, R4 will install two routes into the routing table for the 10.0.1 network. The same will happen for the 10.0.2 network in this example as well. Half the traffic will take path R4 to R3 to R2 to R1, and the other half will take the path R4 to R5 to R6 to R1. You can also achieve load balancing with static routes as well. To do that, just configure two different static routes, both for the exact same subnet and the same subnet mask, but put in two different next hops. Again, that will install two different routes into the routing table, and traffic will be load balanced over both of them. You can have more than two routes if you wanted to. If you put in three routes, it would load balance over all three. Again, something that we covered in the earlier lection when we looked at load balancing for static routing, this is the same for our IGP routing protocols as well. The traffic is not going to be load balanced round robin for the same flow. Meaning if you've got one particular source host that's talking to a web server, for example, its traffic for that one flow is not going to go through the first packet R1, the second packet R2, the third packet R3, and so on. If it gets load balanced to R1, all traffic for that single flow will go through the same router, R1 for our example. But if you've got a different source host talking to maybe a different destination, that will be load balanced onto a different link. So the same flow always goes through the same router, but different flows will get load balanced through the different routers. The reason it does this is we don't want packets for the same flow going over different paths, because that could cause the packets to arrive out of order if there's a longer delay on one path than there is on another, and that can cause some applications to fail. So single flow always goes over the same path. Okay, so that was our equal cost multipath. In the next lecture, we'll have a look at a lab example. In this lab, we'll have a look at equal cost multipath with a lab demo. Now, to start off, I'll use the same lab again where it's unequal cost paths. In this lecture, you'll learn about administrative distance. AD is used along with the metric to decide which of the available paths is going to make it into the routing table. A router will typically only learn routes to a particular destination from a single routing protocol. It's not normal for an organization to be running multiple different routing protocols. When multiple routes to a destination are learned through a routing protocol, the router will install the path or paths with the best, meaning the lowest, metric into the routing table. And different routing protocols use different methods to calculate that metric. For example, let's say we're using RIP as our routing protocol and we want to get to our particular destination, and we've got two different paths to get there. The first path goes from router A to B to C to D. So A to B to C to D would be a hop count of 3, and we've got another path which is A to B to D, which would have a hop count of 2. RIP uses hop count as its metric. It's going to put the shortest hop count into the routing table, so in this example ABD would be preferred. Now we might have exactly the same network topology, but we're using OSPF. And with OSPF, maybe path ABCD has got a cost of 60 and path ABD has got a cost of 100 because the ABD path has got lower bandwidth links. Remember, OSPF takes the bandwidth into account by default. And with our metric, it's always the lowest value that is preferred. So with OSPF, it would be the other path ABCD that would be used, making it into the routing table. If paths to the same destination are received from different routing protocols, if for some reason your organization is running multiple routing protocols and a router receives routes to the same destination from those different routing protocols, then it can't compare their metrics to each other. For example, a RIP hop count of 5 can't be compared to an OSPF cost of 60. That comparison would be meaningless because the routing protocols calculate the metric in completely different ways. It's like they're talking foreign languages, so you can't compare one routing protocol metric to another. The router needs to use a different method to choose when routes to the same destination are received from different routing protocols, and that's what we use the administrative distance for. The administrative distance is a measure of how trusted a particular routing protocol is. If routes to the same destination are received via different routing protocols, the protocol with the best, which is the lowest AD value, wins. So with the metric, the lowest is best. With AD, it's the same, the lowest number is best. And this slide here shows the default AD values of our popular routing protocols. So worst is RIP with a value of 120, then we've got ISIS at 115, OSPF has an AD of 110, EIGRP is the most preferred of our IGPs, it's got an AD of 90, external BGP has 20, a static route has a default AD of 1, and connected interfaces will always be preferred, they have an administrative distance of 0. So administrative distance is used to choose between multiple paths learned via different routing protocols. Metric is used to choose between multiple paths learned with the same routing protocol. The administrative distance is considered first to narrow the choice down to the single best routing protocol, and then the metric is considered to choose the best path or paths, which will make it into the routing table. We can see what's happening with a show IP route command. So show IP route will show us what routes did make it into the routing table. You can see from here, connected routes have got an administrative distance of 0. They're always going to be most preferred. We've also got some routes in here that were learned from RIP as well. And you see the digits in the square brackets, that shows us the administrative distance and the metric. The first value is the administrative distance. We already know that RIP has got an AD of 120. The second value is the metric. So here the first route has got a hop count of 1, the second route has got a hop count of 2. So let's talk through an example. Let's say we've got a router and it receives multiple routes to the 10.10.10. .10.0/24 network, it receives those routes from both OSPF and RIP. So when paths to the same destination are received from multiple routing protocols, the administrative distance is considered first, before the metric. OSPF has got a better administrative distance than RIP, so the RIP routes are going to be discarded. Then the router will compare the routes we've received via OSPF and install the one with the lowest cost into the routing table. If we received multiple equal cost paths, then they'll all go into the routing table and the router will load balance between them. Another thing we can do is floating static routes. Okay, so what I just covered is your standard core information for AD. This is some extra information here. If the best path to a destination is lost, for example because a link went down, it will be removed from the routing table when the router detects that and replaced with the next best route. Now we might want to configure a static route as a backup for the route learned via a routing protocol. For example, maybe we're worried the entire routing protocol is going to go down. A problem if we want to do this is that static routes have a default administrative distance of 1, so they're always going to be preferred over routes learned via an IGP. So if we're running an IGP, we've got IGP routes in there, when we want to add a static route as a backup, that won't work by default because it's going to be preferred over the IGP rather than being the second choice. So how can we make that static route the second choice? The way we can do that is with using a floating static route. When we do this, we change the administrative distance of a static route from the default of 1 to having a higher AD value, an AD value which is higher than the administrative distance of our routing protocol. For example, say if we were using OSPF, and we've got our network topology you see in the diagram here. We're running OSPF along the path from R4 to R3 to R2 to R1, and R5 is not running OSPF. Let's say it's a router that does not support OSPF. So we'll have OSPF being used with the first choice path going along the top from R4 to R3 to R2 to R1, and we want to configure a backup static route on R4 that is going to send the traffic through R5, but only if the top path is not available. So we can't add a normal static route because then it would go through R5 as a first choice. So the command we enter is IP route 10.0.1.0, 255.255.255.0, 10.1.3.2, selecting R5 as the next hop, and then we put in an extra keyword at the end here, we say 115. That sets an AD of 115, which is higher than the OSPF AD of 110, so this will be used as a backup route. Now obviously we'd also need to add static routes coming back in the other direction along the bottom path, and we'd also need a static route going from R5 to R1. Another example, you can also use floating static routes where you're using static routes only. So here again on R4, I could have first choice going to 10.1.1.2, which is on R3. I could have my second choice for the 10.0.1 network going to 10.1.3.2, which is on R5. I would do that by giving it an administrative distance of 5. If I just entered both of these routes without an administrative distance, it would load balance between the two of them. By adding the second route with an AD of 5, it's only the first route that will make it into the routing table. But if the link from R4 to R3 goes down, it will be removed from the routing table and we will use the second route instead. Now, a word of warning with this, if I go back a slide, if you do a floating static route as a backup for OSPF, if any of the links from R4 to R1 go down, OSPF will detect that and the route will be removed from the routing table. So that will work just fine. But with our second example, this will work if the link from R4 to R3 goes down, because R4 will detect that. But if the link from R3 to R2 or R2 to R1 goes down, R1 won't know, and it will continue sending traffic along the top path, and it will only get as far as R3 where the broken link is, and then the traffic is going to fail. So this will work fine if you just have that one router with nothing else along the path, but if you do have other routers along the path, be careful with this one, you could end up causing problems. Okay, so that was our administrative distance. In this lecture, you'll learn about loopback interfaces. A loopback interface is a logical interface, and it allows you to assign an IP address to a router or a layer 3 switch which is not tied to a physical interface. Because they don't have any physical attributes that can fail, loopback interfaces never go down. Loopbacks are logical, so it's impossible for them to physically be in the same subnet as other devices. So they're usually assigned a /32 subnet mask to avoid wasting IP addresses. That's the standard. It's best practice to assign So they're usually assigned a /32 subnet mask to avoid wasting IP addresses. So that's the standard. It's best practice to assign a loop loopback interface on all of your routers and all of your layer 3 switches. The loopback is commonly used for traffic that terminates on the router itself. That could be most commonly management traffic, also for other things like voice over IP, if you need to send voice over IP traffic to the router, also for BGP peering, etc. That provides redundancy if there are multiple paths to the router. You'll see how that works in a second. The loopback is also used to identify the router in OSPF because the loopback address is used as the router ID. So you'll see this when we do the OSPF section. When you're looking at the OSPF database, etc., you'll see routers being identified by the router ID, which is the highest loopback address on that router. The same loopback interface is usually used for multiple tasks. For example, if you need to send traffic to the router for management, and for BGP, we'll usually just have one loopback interface and use the same IP address for everything. Multiple loopbacks can be configured though. It's not common, we don't normally do that. It's usually only done for special use cases where an additional loopback is required, so not standard. Okay, so here you'll see an example of why we're using a loopback. We've got a PC, let's say, which is behind router R4, and it's got IP address 10.1.2.10. And we want to connect to the R1 router to manage it. Well, we've got two paths that we can get to R1 via R4 from. We can either go along the top path or we can go along the bottom path. But if the top path goes down, we can't connect to the 10.0.0.1 IP address on R1, it's down. If the bottom path goes down, we can't connect to 10.0.3.1. So we're going to use a loopback, so that way we get a single IP address that we can use to connect to R1 even if one of those paths goes down. So what we do is we add interface loopback 0 and we give it IP address in our example 192.168.1.1/32. You can use any IP address you want for the loopback, and we then advertise that in the routing protocol. R4 will then learn the two paths that it can use to get to 192.168.1.1, and it will use whichever one has got the lowest cost, or both if they've got equal costs. And R4 can still connect to 192.168.1.1 even if either path goes down. So this is useful for management, and it's really critical for other things like BGP and IP telephony. Let's say that we're sending IP telephony traffic from behind R4 to R1. We want to make sure that it's always going to get there even if one of the paths goes down. So we don't direct it at a physical address on R1, which can go down, we direct it at the logical address. And that way, even if one path goes down, the traffic is still going to get there across the other path. So that's why we use loopbacks. So let's configure this in the lab. It's going to be a quick and easy lab. I'll do it right now. So I'm going to put the loopback interface 192.168.1.1 IP address /32 on R1, and we'll see how R4 has got the two paths to get there. Okay, so I'm on the lab, I'm on R4 here, and I'll just check that I've got EIGRP running everywhere. So I'll do a show IP route, and I can see I've got an EIGRP route going out fast Ethernet 2/0, which is via R5. and I've got other EIGRP routes going out fast 00, which is R3. So I want to have two different paths available with one IP address that I can use in 5.25 to check my 119. Recent CRP trail using that same IP. In this lecture, you'll learn about adjacencies and passive interfaces. Our interior gateway routing protocols, so RIP, EIGRP, and OSPF, are configured under their global configuration, and then they're either enabled or not on the router's individual interfaces. When the routing protocol is enabled on an interface, the router will look for other devices on that directly connected link which are also running the routing protocol in order to peer with them. The router does this by sending out and listening for hello packets for that particular routing protocol. And when a matching peer is found, the routers form an adjacency with each other and exchange routing updates with each other. Modern routing protocols use multicast for the hello packets. This is more efficient than broadcast that was used by earlier protocols like RIP version 1. With multicast, it's specific to the particular particular routing protocol. So a device is only going to process that packet if it's interested in forming an adjacency with that routing protocol, unlike broadcast traffic that has to be processed by all hosts. So it's more efficient. Okay, an adjacency example. So here we've got router R1 in the middle, and RA, RB, and RC. And on R1, we've got a loopback configured there with IP address 192.168.1.1/32. The IP subnets configured on the interfaces, which are enabled for the routing protocol, will of course be included in its routing protocol updates. For example, R1 here has a routing protocol enabled on the loopback 0 interface and interfaces fast Ethernet 0/0 and 1/0, but it's not enabled on fast 2/0. The reason we've done that is that RC belongs to a partner organization and we need connectivity to them, but we don't want to be sending internal network information to them. That would be a security issue. R1 will send out and listen for hello packets on the loopback 0 interface and fast Ethernet 0/0 and 1/0, because those are the interfaces that we enabled the routing protocol on. And it will form adjacencies with any routers that are running that same routing protocol that it finds on those links. So in this case, we've also enabled the routing protocol on RA and on RB on the interfaces that are facing R1, so the routers will discover each other through the hello packets, and they will then form an adjacency and share routing updates. But R1 will not send out or listen for hello packets on fast 2/0 because we didn't enable the routing protocol on that interface. So it will not form an adjacency with RC. It's not going to be giving out any network information to RC. So in the example here where RC is a partner, we need to have connectivity to them, but we're not going to be giving them out internal information. In that case, we could use static routes between us and them just to give very limited connectivity. An adjacency example, so the same one, R1 will advertise its IP subnets to RA and RB because it formed adjacencies with them. So it will advertise the 10.0.0.0/24 subnet, 10.0.1.0, and 192.168.1.1/32 its loopback. But it will not advertise 10.0.2.0/24 because that interface was not included in the routing protocol. When you enable a routing protocol globally and then you enable it on an interface, the router will try to form an adjacency on that interface by sending out hello packets, and it will also advertise the subnet that is on that interface as well. But if an interface is not included in the routing protocol, then the router won't send hello packets out there, and also it won't advertise the subnet configured on that link to other routers either. So in our scenario here, we're not going to be sending information to RC, but also RA and RB will not learn routes to 10.0.2.0/24 because we didn't include it in the routing protocol. So what if we do actually need RA and RB to learn a route to get to 10.0.2? That's where passive interfaces come in. Passive interfaces allow you to include an IP subnet in the routing protocol without sending updates out of the interface. So here, if fast Ethernet 2/0 is configured as a passive interface, RA and RB will learn routes to 10.0.2.0, but internal network information will not be sent out to RC. So that's what we wanted to do in this situation. It's best practice to configure your loopback interfaces as passive interfaces, always. So this is nothing to do with giving out network information on them. This is because it's impossible to form an adjacency on a loopback interface. It's impossible for another router to be directly connected to the loopback interface because it's not a physical interface, it's just logical. So there's no way we're going to ever form an adjacency on a loopback. Making the loopback passive means that it will be advertised by the routing protocol. So we want to do that. We want other routers to learn how to get to the loopback, but we don't want to waste resources sending out and listening for hello packets when we know that there's never going to be another router connected in on that link. So this makes things more efficient. Always make your loopbacks a passive interface. So the use cases for passive interfaces, to summarize that, we use them on our loopback interfaces and also physical interfaces where the device on the other side belongs to another organization, or maybe it's not another organization, but the device on the other side, we don't want to send routing information out to it, but we do want our other internal devices to know about that link. Okay, so that was the theory for our passive interfaces. Let's actually configure them in the lab. We'll do that in the next lecture. In this lecture, I'll tie together the information that you already learned in this section and clarify how a router decides which route to use for any particular packet. Routers learn routes by an administrator configuring IP addresses on its interfaces that will generate connected and local routes, and by an administrator configuring static routes on that router, and also by receiving routes via routing protocols from neighbor routers. So in the example here, we are going to be configuring R1, and on there we configure interface gig 0/0 facing over towards R2, and we've given it the IP address 172.16.0.1/30. We are also optionally configuring a static route on this router as well. I've said IP route to 192.168.100.0/24. The next hop is 172.16.0.2, which is this interface here on R2. And in this example, I'm also running RIP between the two routers, and R2 has advertised its 192.168.0.0/24 network over to R1 using RIP. We'll cover the configuration for our different routing protocols later in the course. So if that's the configuration that we have got on R1, if we then do a show IP route, we will see routes for all of those showing up in the routing table. So we've configured the IP address on the interface, so that's why it's generated my connected route here to 172.16.0.0/30. That is the IP subnet configured on the interface, and then the actual individual IP address that I'd configured on there was 172.16.0.1. That generates my local route. I've also learned a route via RIP from the neighbor R2 That's going to 192.168.0.0/24 with the next hop on R2 of 172.16.0.2, and I'd also configured that static route to 192.168.100.0/24, again pointing at R2 at 172.16.0.2. Okay, so that's how the router can learn various routes. Then how is it going to decide which route to use whenever it needs to forward a packet? A router's main job is to forward packets received towards their destination. Based on the packet's destination IP address, and it decides where to forward a packet based on the routes that it has learned. The best route for a packet decision is based on first the longest prefix, which is the most specific route, then it is on AD, administrative distance, and then it is on the metric. I'll be explaining this in detail as we go through this video. If a router learns multiple routes for the exact same network and prefix, it must decide which is the best route out of them. For example, if it's received a route to 192.168.0.0/24 via EIGRP from R2, and it's also received a different route via OSPF from R3, For that same networking prefix, 192.168.0.0/24, again, it has to decide which is the best out of these two routes. So when I say the exact same, I mean the network is exactly the same. 192.168.0.0 in this example, and the prefix is also exactly the same, /24 in this example. If I'd received one route for 192.168.0.0/24 and another one for 192.168.0.0/26, for example, they would be different. So I'm talking here about when it is exactly the same network and prefix, and we're learning multiple ways to get there to that exact same network and prefix. So only the best route for each learned exact same network and prefix makes it into the routing table and is used to forward packets. The criteria which is used to decide which is the best route is, first up, the administrative distance. A lower value, a lower number is better. And if there is a tie, meaning I've received multiple routes to that same network and prefix with the same administrative distance, then we need a tiebreaker, and we use the metric as the tiebreaker. Metric, also known as the cost, you want a lowest cost possible. So again, just like administrative distance, with the metric, the lower value is again better. If there's multiple best routes which have got the same administrative distance and metric, so they're exactly the same, if they're to the same network and prefix, they've got the same administrative distance and they've got the same metric, but you've learned multiple routes with those exact same values, then they will all enter the routing table, and the router will perform equal cost load balancing over those different routes. Okay, so let's look at some examples just to make sure that everything is explained really clearly. And the following examples are based on this network topology here. Now, with this network topology, you would never see this in the real world. You would never have RIP, OSPF, and EIGRP all being used in the same network. You're also going to see that there's a lot of overlapping routes being received as well. I'm just doing that so that I can clearly explain to you how the routing precedence works. Okay, so don't think, why is the network designed like that? Okay, real world, it would not be. It's a crazy network. I've just done it like that so I can show you how routing precedence works.
Okay, so the first example, R1. So looking back at the diagram here, it's always going to be R1 that we are looking at. And it's going to be learning routes to get to destinations over here via R2, R3, R4, and R5. So in this first example, R1 learns these routes. It learns a route to 10.0.0.0/24 via RIP, which has got an AD of 120 from R2, and the metric is 5. It also learns another route to the exact same network and prefix, 10.0.0.0/24 via OSPF, which has got AD 110 from R3, and that route has got a metric of 2. It also learns a route via EIGRP. EIGRP always has an AD of 90 from R4 with a metric of 3072, and it also learns a route to the same network and prefix, again via EIGRP, which again always has the AD of 90 from R5, and that route has a metric of 6144. So again, looking back at the diagram here, all for the F with administrative here, with a route via RIP routes or so the D designates this as N, which so 2. It is from R either, so all addresses have mainly 0.68.0.that one router out enter only man is you put out interface, and if R out 10, so we're going to be moved from here.
In this section, you'll learn how to troubleshoot network connectivity issues. Usually, the first way that